Right, so hello everyone, I'm Mark Dawson. I'm going to talk a little bit about Git today. It's not an introduction, but we will only cover the basics. So we'll only cover the things like add, commit, but the idea is to give an idea of how Git does them rather than how we do things with Git. So it's not a talk about features or things we can do with Git. It's more a talk about how Git does the things that we probably already do. So Git basics. What is Git? I'm assuming everyone here, most faces are familiar. I'm assuming everyone here uses Git, has used Git. Yeah. So it's a self-acclaimed steep content tracker. That's what it says on the man page. I quite like that. I think lots of things about Git make more sense when you start thinking about it as a tool that's written by developers, a developer, set of developers, for other developers. So once you get into the mindset of thinking, if I was writing myself a couple of scripts to do the kind of things that I do with Git, what would I write? All starts to make a lot of sense. One of the main differences between Git and some other content management systems, or the more traditional content management systems, is that it stores snapshots of your entire current working directory. It stores entire snapshots of all of your files at any point in time, rather than storing just deltas, which is the way that with a more traditional approach for content management source control systems. And the other thing is that it does everything locally, so we're doing what we call a distributed source control model. And I've heard this many times, Git described as a leaky abstraction over some underlying data. So there's some underlying way of storing the changes that we're making and the changes that we, and the revisions of certain files in our file system. And we've got a fairly thin and pretty transparent layer on top of that. It's fairly easy to see through. So I think it's really starts to make a lot more sense once you understand what the data model underneath is. Those commands themselves start to make a lot more sense. So what do you mean by deltas? This is straight out of the Git SEM, the open source book, which is very good if anyone wants to have a look at it. So this is the more traditional version. I have file A, I change it, I store the changes, and then it might not change for a while, and then in version 4 I might store the changes again. Git does things a little bit differently. I say I have file A, well in version 2 I haven't done anything, so I store, it sort of just refers to file A. Here it just refers to file A. And here eventually I've got A2 where I've made some changes, but rather than store the difference between the two, I'm just going to store the whole thing. This turns out to be quite good actually, in ways that we'll hopefully have a think about and see in a little while. The other thing to note about Git, so these are just a little bit of an overview of the sort of basic things, is that it's a directed acyclic graph. You can't really go to many talks about Git before running into this term, and it essentially means that most of the meaning's in the title. So it's directed, i.e., all of the
arcs.
Pardon?
The arcs.
The arcs. All of the arcs have direction, and none of them go round in circles. Essentially, so I can't get from A to B to D and then back to, for example, A again, which sort of makes sense for content management. Time doesn't work like that. Time goes forward, so we can't have a commit in the past that depends on a commit in the future. The other thing that you're probably mostly aware, if you use Git regularly, they've got 3 staging areas. I put these slides in a little bit in case there was anyone who was a little bit less familiar. I think I can probably be fairly brief on this. So you've got a working directory, which is your files that you're working on. You've got a staging area that you move the files into, so you can create some commits that aren't just all of your files. And then you've got the actual repository, which into which you create commit objects. And finally, everything is local. So I make some changes, someone else makes some changes. Well, the idea is the green are is some repository that exists. I download it, I make some changes, someone else makes some changes. They might not necessarily be at the same time. Seeing as we've stored the snapshot at every point, it's quite trivial to see that that's virtually equivalent to this. So we can go and grab just the changes, just those snapshots of the directory from the other person, and we can construct something like this. We'll go into detail of how things point backwards, etc. in a moment, and then we can sort of go and merge things. The part of the idea behind Git is that this sort of branching and merging is supposed to be very easy and supposed to be completely independent. Now, one of the instant problems that you see here that we don't necessarily have in centralized source control systems is how do we then go and number these commits. If we number them sequentially, which possibly would be could be the simplest way of thinking about this. We then need a centralized service to dish out the numbers. So I need to be constantly connected to some centralized server that's going to constantly dish out the numbers. So that's not very good. I could say, hey, I'm going to dish out identities once. I'm going to be Bob, you're going to be Alice. We're going to namespace all of our commits with Bob1, Alice1, etc. That could work, but it still requires the connection. It still requires this central server. We can maybe do a little bit better. We could start thinking about UIDs or random numbers. They're starting to get pretty good. So now if I have a random number and I know that there's a very small likelihood that someone else is going to generate the same random number, we could both generate commits. We could label them with random numbers, and then we could have names for them to pass them around and for them to refer to each other. Yeah, so these numbers aren't just for humans; they're also for the machine to be able to identify bits of data on different machines as they get passed around in a unique way. So that's one interesting question. Then is what if we look at this graph here and actually 5 and 6 change the same file in the same way? Should the content management system handle that in any kind of different way? Good question. So Git actually does something really, really clever and takes this a little bit further and essentially addresses all of the commits by their content. Right? So the idea of a commit is a unique enough fingerprint for content, for everything in that commit. Content means file names, locations, contents of the files, times of the commit message, commit author, and parent of the commit. So once I have all of those things, that will always, and all of the content of the file, of all of the files, that will always produce the exact same commit ID, which is a really interesting concept. And obviously changing all of these will change the commit ID. So we've got a fairly good, we're fairly sure that the commit is going to actually correspond to the commit. Once we have a commit ID, that the content is going to correspond. Git goes a little bit further than that, and the commit itself is a tree as well. So the commit is, if we think the green dot is the commit, then these purple triangles are what we call tree objects. Yeah, so essentially there are three type of objects in Git. There's a commit object, there's a tree object, and there's a blob object. The blob is essentially a file. It's a batch. It's not a file. It's a bunch of content that would reside within a file. So the contents of a file, and then we have these tree objects that contain the directory information, and also the naming of the files. Yeah. And then we have the commit objects that points to a tree object that contains a bunch of either blob objects or tree objects. Right? So in this way we can construct the entire tree as we would. The nice thing about this is that we can, if we have two files that have different names in different places with the same content, we can refer to them only once. If there are two files anywhere in the repository, in any of its entire history, in any directory, anywhere, that have the same content, it will be referring to the same object. Yeah? So if I go, as an example, if I create a new commit where I'm going to move this directory, remember these are essentially directories, I'm going to move it up to here, right? So over on this side, I can see that I've coloured the white things that are the things that don't change. They're not stored in this commit. The blobs aren't. They just refer to the previous commit. So now all I'm storing that's new is this tree object, because it now contains a different listing. And obviously this tree object, because it contains a different listing. The files are all referred to from the previous commit, which is really, really sort of powerful, really. Because you can really ensure that you don't get any duplication. And it's fairly easy to do, because everything's referred to by its unique fingerprint. So, and everything's addressed by its unique content fingerprint. So if I try and store something in the same content fingerprint, I'm trying to shove it into the same place. So, so this, we don't really have to put any effort into making this happen, or very little effort at least. So that's one interesting. So that's how these objects work. So I'll take a quick look at the three types of object, which are the commit, the tree, and the blob, and what's actually inside them. So this is a commit object. There is a file within your .git directory that contains this. Literally this. Yeah? Or very nearly literally this. It'll tell me the tree. So that's the base tree that we saw. It'll tell me its parent, because this commit might be based on another commit. So we need to know where, if we want to build our branches, we need to know where it came from. It'll tell me the author and the time, the committer and the time, and the commit message. Right. From this, essentially we're using SHA-1 hash. So based off this content. So if anything in here changes, the commit's going to change, right? The nice thing is that this is the tree object. It's got permissions. What is the child? This could be a blob or a tree. The hash of the content, which is nice because we can now validate that the content is the right content that it should be. And the name of the file. And so notice the name of the file isn't related in any way to the content. Right? So that's the tree object. Now notice this is interesting because this doesn't have any concept of time or committer or author or anything like that. So if I don't change those things, then that stays. This tree object is a little bit more reusable maybe than the commit objects. And then the blob object, in my case, is a file containing the word cool. So that's what's in the blob object. Right? Now these are files we'll have a look at in a second, and they're just there in .git. So essentially, that's what Git does. It's pretty much taking copies of the things we have in our working directory and copying them to a place in our copying the content to a place in our objects directory inside the .git file, and then it's creating these trees that correspond to the directories, and it creates these commits that contain the trees. That's it. So I lied a little bit. It's not quite that simple, but it's not far off. There's a single word text identifier at the start of each object and the content length. So instead of cool, it actually says blob for cool. Right? Also, it's compressed. Right? But it's compressed with sedlib, so it's fairly easy. It's not difficult for us to get back. And that's pretty much it. So for the blob object, instead of that, if I decompress the file and look inside of it, that's what I see. Right. So, part of the idea here is to see how close to the surface the things that Git does are, and how easy it is to just dig in there and do things, or see things. So because we've got this unique fingerprint, we get lots of things that are virtually for free or fairly cheaply. Validating the integrity of the content is easy. Data corruptions are very, very easy to detect because everything is identified by its hash. Anything that changes at any point, we'll know it almost straight away. Making malicious changes and trying to push those into repositories is very, very difficult. For starters, because we've got this number, so we've got the length. So not only do I have to reproduce something with the same hash, which has been done for SHA-1, so not impossible. I also have to do that with the content being exactly the same length and the thing making sense in some way that it's advantageous to me. So it's very secure. Avoiding file duplication, as we've seen, is fairly trivial now. And comparing huge source directory trees, comparing loads of files, it's really simple because if I want to see if the content of two gigabyte files are the same, I just look at the two hashes, and if it's pointing to the same file, they're the same. If it's not pointing to the same file, they're not the same. I can know instantly by this 40 character number that everything is the same. A little bit of misdirection. Well, I've done the plots, the graphs that I've drawn so far, the branch graphs that I've drawn so far. The arrows have all been pointing forwards in time, but actually we've seen now that they point backwards in time because a commit refers to its parent. Actually, a commit can refer to more than one parent. Which makes sense, which is what you get with merges. So if you look inside the commit of a merge, you'll see parent, and you'll see multiple hashes or commit IDs. And this makes a little bit more sense because we're far more interested in knowing where a commit came from than where a commit, or all of the places that commit could possibly be going, which is interesting. But it's not very human-friendly in the form we've described it so far. We've essentially got a giant bucket of spaghetti to some extent, and even worse, spaghetti with multiple heads, and we just don't know what's what. Yeah, I mean that's the easy way of thinking of Git, is just a big bucket where you throw content into, and some of the content refers to other bits of content, forming chains. So we need a slightly more human-friendly way to say what we're working on, particular parts of these chains that we're interested in, bearing in mind that Git, to a point, in the short term at least, doesn't really delete things. So all of these things that we've tried and reset and gone back and moved around, they're all still there in this lying in this soup. So the solution is surprisingly simple, as everything else with this, as many other things with this content management system. We create a text file and we put a commit ID in it, right? We call this a branch. We store them in a location, and whenever we create a commit, we just write a new commit ID into this branch, into this file. Right, and we can see these files in a second, and we've essentially solved the problem. So the only major, well, I don't want to say that, but the biggest thing I think we haven't mentioned so far is the index. The index is a little bit different. It's not as simple as these compressed text files. It's just a binary file with some info on the index on the files in your working directory in the state that they're supposed to be in the index. As you can imagine, if it needs to refer to things that change in the working directory, it will then go and create blobs for those. So essentially, if I'm adding a file to my index, it's at that point that it will create a blob object, which is the content. Then the index will essentially act as the equivalent of maybe my commit or my tree, in that it contains a list of the file names and references to the blobs of content. Yeah, because they could change as I'm editing, and Git needs to remember the way that they were at the specific point in time. The interesting side effect of that is if I add something, and then I add it again, and I add it again, actually all of those times I added it, even though for most people's day-to-day Git usage it appears to be lost, all of the data is still there, because it's still created all those blob objects. So if I want to go back to 3 adds ago, I can do that. Right. So I'm going to show you where all this stuff lives, just so we can have a little bit of a dig into the .git directory. Okay, so we create demo was what I was trying to go for, and change into it. Right. So if we look what we've got here, and we have a quick look inside Git. You don't have that, of course. So we can see that we've got branches config head. Hooks has some stuff in it, but we're not particularly interested in that right now. The one we're really interested in are objects and refs. So all of the objects that we saw previously, the tree, the commits, and the blobs, are all going to be stored in this objects directory, and they're going to be stored according to the hash, so according to the fingerprint that we saw. Yeah, according to their SHA-1. Refs is going to contain refs heads that we saw. That's where the branches live. So once we start creating branches, we'll be able to see them there. And head is, we're all familiar with what head is. A head points at the current branch head. Okay, so I'll do some stuff, I think. So what I can just ask for a second. So can you check how much battery there's left? I can write down to. Yes, of course. 34. I don't know how long that means.
It looks bad, but it doesn't sound.
34 sounds reasonable.
All right.
See if we can go quick. Any questions? But there's people familiar with that stuff or not so familiar? Newish. Okay. Let's have a look. If I go into the, what I'm going to do quickly is, sorry. And okay, cool. Right. So the first thing that we could do is create some content, create a file. So if I go something echo hi into hi.txt, so I've got a file there now. As we can see, nothing's getting created in the objects directory yet. If I go git add hi.txt, I can look in the objects directory, and I can see that I've created a file there. So that's 45 followed by the hash, but by the rest of the hash. So the hash is divided into the first 2 characters, which are the folder name, and the rest of it. So the other 38 are then the file name. We can do lots of. We can have a look inside of this. I've gone and written a few line script, which is very, very simple. The first section here is essentially just figuring out where the path is. So figuring out where that file is based on some ID. It's not really doing anything. Then I import the zlib. I open and read the file. I decompress it, and then I print it to the screen. Right. I've got some dividers here with the dotted lines, and then just so we can confirm that what we think is true, I've gone and created the SHA-1 of the decompressed content. Right. So it's fairly simple. So I should be able to do something like decompress get object 25b, and voila. So we can see inside of that content was the hi that we said. It is literally just storing that file. So it's very, very simple. Blob 3, we've got a null character, which we always have, and then the new line because it was an echo, so there's a new line at the end. And we can see 3 because there are only 3 characters. We can see here that this hash that we got from the content is the same as this hash we see up here. So bear in mind that this hash is the hash of the content plus the prefixed string. If you ever try to recreate this sort of stuff yourself. So that's one thing I could do. The other thing I could do is I could say, well, let's go and add to that again. So I've got hi. Oh, sorry. What am I doing? So I've got hi again. So I do git add hi, and then status. Well, yeah. So now we've got this. We've added again. So maybe we're thinking we've lost that bit of content. But if we look inside the objects, we see that we now have 2 separate blobs. We have 2 bits of content. Notice at this point we don't have any trees. We don't have any commits. We have nothing. We just have the individual bits of content. That's because all the metadata is stored in the index, which we'll look at in a bit. In fact, I could have a quick look at it now. The index is a little bit trickier. You see this index file in there. That's where all the index, the staging area information is kept. If we try and do that, I get some not very friendly output. That's because it's a binary file. You can find the formats if you look in the Git documentation. It stores a fair bit of information on each file, so it's a little bit less easy to dig into than some of the other objects. But we've got this ls files, and if I give it a stage, that will tell me the files that will list the files in the index. If I give it a debug flag, it gives me a little bit more information. It tells me a little bit more of the things that the index can see. So it can see things like the modified times, the inode number, size, things like that. So some fairly useful information there. So that's a little bit on the index. We can also, an interesting thing to do is that we can actually create these objects ourselves. So we could go. Git has a few useful lower level commands. I won't go into too much detail. Cat file is a useful one. So I can say cat file 2f28, and that will show me inside of this 2f28 4e, inside of that file that we committed, will show me the content. Maybe a more interesting thing to do would be to look at the content of the previous commit that I supposedly can't access anymore. So 45b9. And that's the previous content.
Can I ask you a question?
Yeah.
What happens if you mock one?
If I mock one,
Yeah. If we just put one into the object tree by hand.
well, there's several ways you can do that. You could either create it yourself using basically the Python script I showed you backwards.
Yeah.
Or you could create it to your, there are Git commands to do that. So you could do something like Git. What is it called?
My question was basically the thing I fear.
Oh right, okay. From a sort of security point of view.
No, not really a security point of view.
Corruption.
I'm mostly just curious. Yeah. What happens if you sort of put one in there by hand? Because if you use an underlying Git command, it might update the index somehow.
Oh, I see what you mean from the point of view of the index.
Yeah.
Right. So the index is a bit trickier.
Sure,
Yeah,
but that's sort of the question of what happens if you just put a file in the objects folder that is the correct format.
The file exists in the objects folder.
Yeah.
I mean, this is how Git works. There's basically a big bucket of objects, and the objects point at each other. But
the question is sort of how would
if they're used in some sort of sensible way. Yeah. So if you just put an object in the object file, I can do that.
But it has to be the correct.
Does it? Will Git care if you put a file in the object tree that doesn't follow its format?
I don't know.
Okay, yeah, you could just put something that doesn't follow the format, but there's this command essentially. So I've created more stuff. I'm not even going to create a file.
Okay.
This is just the string more stuff. It's going to go into a blob, and it's going to get written into the database. Right?
Yeah.
That's the ID. If I look inside, let's go find. There we go. It's in the database.
Okay. Sure.
Right? Okay. At the moment, it doesn't really do anything. Right? Because I haven't added it to anything else. Right? So I need to either add it to a tree, which is pretty easy to do. I just create a tree object that references this.
Mm-hmm.
Right? I can do that either just by writing the tree file in the right format and then compressing it with zlib, working out the hash and putting it in the right place, which you could do fairly easy with a little script. Or there are Git commands that will help you do that. Right? So you could, and then I could put that tree in a commit, and I could even reference a previous commit, all just using Python or the shell or whichever tools you want. Right?
I assume how it makes sense is basically the fact that the 45b9, like this file exists, or the 2f, I guess, which is the actual file. The reason Git knows about it is because when you added it, it also updated the index.
That's right, yeah.
Which is
So
where it has this tree that references all the
yes. So the index is a little bit trickier because it's binary, so you wouldn't be able to just write a text file and compress it, but you could do fundamentally the same thing.
So what happens if you've got a file in the database, in the objects folder, that is not referenced in the index when you push?
Chances are, when you push, you will have a lot of files that are not referenced by a lot of things. There's lots of dangling changes every time you do a reset, every time you step back a commit, every time you do commit amend, you're creating dangling commits and dangling objects. What Git does is after, I think by default it's 2 weeks. So after 2 weeks, it'll look at files older than 2 weeks and it will clean them out, right? You can change that, of course. Yeah, and that's it. When you're pulling, you just pull in a bunch of files and with references. It's
Yeah, but I guess
yeah.
on push, does it use the index to work out?
Yes, sorry.
Just
Yes.
STP
The
entire
index.
folder?
The index is used in the context of index staging area. Yeah, so that's what we mean by index. We don't mean index as in database index. There is no database index. All objects reference other objects directly. There's no
So-
indexing as such.
So does it, when you push, does it walk through the tree?
Exactly.
Or does it just go into the object folder and say, I'm going to push everything in this direction?
So when you push a branch.
Yeah.
Yeah. So the branch, remember we said was a text file that points at the commit. So it looks to the commit. It walks backwards. Yeah. And it and it works out what it needs to do. I have a few more slides actually that will maybe clarify some of this stuff.
So, just to be 100% clear, that means that if you know were to make a commit and push that commit, your 45B9 file will not be pushed. This object.
Yes. Along with all of the other scrappy little changes that you've made locally, all of your stashes are commit objects. Yeah, so they'll all stay locally. They're all just objects floating around in your objects directory. So Git, when it pushes, will decide what to push, and will push those things that it needs to push, based on walking back through the tree. Okay, so what I might do at this point, we've seen that we've seen adding, we've seen the index, we've seen a little bit of these objects. We haven't committed anything yet. I'll do a commit, and then we'll walk back and talk about things like the rebasing and merging and all that sort of stuff. So if I do...
Can you actually see the content of those files with the script that you...
Yeah, absolutely.
Yeah, just do...
So I've got another script, which I'll show you, which is this that I've written for the sake of today, which I thought would be a very useful script. It does basically exactly what we're doing now. Yeah, it looks a bit more confusing because it's using the Git plumbing commands, but essentially this first command fetches all of the objects. Yeah, it's going to fetch all the objects. I've sorted them because I like to see the blobs first and then the trees and all that sort of stuff. Then I'm going to put it into a directory. Then I'm going to output to the screen the current object, just cat.object. And then I'm going to do a little diff with the previous objects so that I can see what's new. Yeah, so I thought that's sort of a useful thing to do. So if I do objects here, that shows me all the current objects. So I could do something like graph blob do something like, there may well be an easier way of doing this. It's just the first thing that's coming to my head. Git cat file p, and then I do that, and then I'm going to go and put some limiters so we can know which one's which. That should roughly work. If anyone can see any reason it might not. Yes. What have I done wrong? F, isn't it? No. Okay, so what that's done is from this object, it's got the 3 object IDs. Oh, you want to see it decompressed, don't you?
Yeah.
Which is basically the same thing. Decompress.
Not gonna work. Oh, okay.
So this is the script. You can see the equal signs between each. This is the... Can you see my mouse? Yes, you can. So this is the string that comes out of each. That's what's inside them.
Okay. So no reference to the file name?
No reference to the file name yet, because we haven't made a commit. Right?
Okay.
The objects, there's 3 types of objects. Blobs, which are content, and just content. Trees, which are the directory structure and file names. So basically, trees are the structure of the content. Yeah? And they can be organized in a hierarchy. And commits, that point to the top tree of the hierarchy. That's the data structure. Right? When we add content. Right? And then we tell the index, we don't create trees or commits, because otherwise we create trees or commits every time we added anything or changed. You know, if I did an interactive add with a -p, I'd be creating, I could probably create 20 trees and 20 sort of trees and commits in one go. So we add it to the index. Yeah? And the index doesn't have any concept of history really. It's just, this is the current state of the index. When I change the index, I just change that file. The idea, I guess, being that we don't care about the history of the index. But the index, but the way it works is that the blobs, the content is created straight away, with the idea that then when I create a commit from the index, most of the hard work's already done. All of the hashing, all of the heavy lifting was actually done in small bits and bobs along the way as I was doing add. So when I say commit, all it has to do is take the index and copy it to the directory tree structure on the commit. Okay, so and actually in some cases, if the tree structure, some parts of the tree structure are still the same, it doesn't even do that. It's just going to refer to the top of the tree structure that hasn't changed because it's already there. So if we just to remind ourselves, this is when we did the stage. We did that. That's showing us what's inside the index. Right? Does that answer the question?
Yeah, no, just.
Okay. So where were we? Right. Is that relatively clear then? What's happening with adding files at least? I'll do a quick commit, just so we can see that. New commit. And if I run my object script, I've got some new stuff. Yeah, so I've done the commit now. I now have a tree object, which I can see in here. Tree, so C982, C982. And I've got a commit object, so O3AB, O3AB. Yeah. So these are two new objects. I can't really tell them apart just by looking at the file system. All objects are objects. They refer to each other, and we have this tangled web of references. But we can use the git commands to inspect them and tell us what they are. For example, so for example, git cat file t will tell us the type of the file. I should be able to do 45b9. It's a blob, right? So we have ways of inspecting this. So that's interesting. We can look inside these now. We can do decompress with our decompress script. Objects C9 82. So look inside, and we can see. Oh, this is a tree. So it's got tree. As we said, and then the length. So as we said, all of the objects are prepended by their type and length. Yeah. This makes it really difficult to corrupt anything, because any corruption, to maliciously place any content, because any content has to be exactly the same length. Then it's got the permissions, the name of the text file. It's got this null separator, and then it's got. This is actually the hash, and because we've decompressed it and it's not, I assume because it's not written in hex, possibly. I'm not entirely sure on that, but that is essentially the hash there at the end. So we can do, if we do the same thing with git cat file, -p is pretty print, so it'll take any object and show me some representation of it. The nice thing, as a side note, the nice thing about Git is this dereferencing stuff. The first thing it does with anything you put in is it tries to turn it into something. It tries to dereference it to maybe a commit or some sort of object that you can look at. So I've got this. So yeah. Here we go. Inside of the tree, we've got the same information there displayed by the cat file. We can do the same thing for the commit. So if I go back to objects, so my objects command, and this is the commit that we just created. We can have a look at that. 03AB, and that is the information that Git says is inside the file, and we can check up on Git if we want, using the stuff that we've written, and we get C982. I still haven't. I should have written this to dereference the things as well. It's quite easy to do, but I thought that would maybe confuse the issue a little bit. So here we have essentially the. Oh, that's wrong. Sorry. That's the tree object. My fault. User error. So here we have essentially the same information. We've got the type, the length, and then this is the text that we just saw. Yeah? So it's really easily accessible. It's really close to the surface. You can really quite easily go digging in either with the Git commands or with your own commands. In terms of the index, you were asking earlier about the index. The index we can write to the index as a Git update index that will get rid of all of the pains of us having to deal with the formatting if we really wanted to just write things directly into the index. And all of these blobs, trees, commits, we could just create our own, as long as we create the right structure and we point to the right things and put the right text in the right place. Cool. So I'll just quickly jump back to the presentation. So now that we've had a little bit of a flavour of how that works we've seen it ourselves a little bit more. I'll go into the slightly more maybe difficult parts, let's say, but actually now that we understand the internals, we'll find that the difficult parts are actually also fairly easy. A three-way merge, right? It's actually now really simple. I've got two endpoints that are referenced in some way. One thing I didn't show you was branches, but that's fairly straightforward. It's just a text file with the commit ID and heads. The head is just a text file with a reference to the branch. So they're very, very straightforward. So now we have these two endpoints, and if we're trying to merge them, all we do is walk back along the tree until we find a common point. That's now easy. We just keep following the parents. Once we find a common point, we have what we call our merge base, and we have two endpoints. We just do, and you can see how when we have the content from the three, at least for a single file, and for multiple files, the concept is the same. A merge is dead easy. I just look at what's changed from here to here and what's changed from here to here, and I apply them both. If they both happen to be on the same line, I do nothing. I just say to the user, you think about this, I don't know what happened, right? When I jump back to the terminal, I'll show you how you can, it's quite easy to actually grab these files, grab the object IDs of all of these three files, look at them, play with them. And you could use those object IDs in any way that you'd normally do things, so you can run logs from here or run whatever you want from anywhere. So that can be quite useful. So merging's pretty easy. Rebasing is also fairly straightforward. We find the base commit again, compute the patches, apply them one at a time. This is actually, for me, I think one of the things that I was surprised how simple it was. We've got these two endpoints. We've got the merge base. On one, we walk this tree back. On the other tree, we just compute the patches. We compute the diffs from one to the other. There is a directory in .git where the diffs are stored as text files, right? One at a time, we walk through and apply the diff. And then the next one and apply the diff until it breaks, right? You can even go into that text file and manually edit those diffs if you really feel that you want to. And it still works. Because all it's doing is reading that text file and applying those patches. It's just applying patches to a file that it already has. So that's. I'll run through an example of that in a second. Resets. Oh, for some reason these have gone. I thought I'd throw this in, even though it's possibly not in the scope of this talk, because I find that reset and checkout are one of the most confusing things about Git. Even when you understand it, there's still which one to use. It's still quite confusing. So reset operates on a branch level. That's the main thing. And checkout operates on the head. Yeah. So we have a branch, we have the branch file, remember, which just contains the ID, and then we have the head that is basically telling us where we are right now, and that's a pointer to a branch. Yeah. So we've got two layers of indirection, if you will.
Well, you can actually have a head which points to no branch, right?
Right.
In that case.
Yes. A head that points to something.
Yeah,
Yes.
okay. But usually branches. Okay.
Yeah, usually a branch. Okay, yes. No, very good point. Your head could be pointing to nothing. And in fact, you could point your head at pretty much any of the commits that you've created, even if they have no relation to anything else that's going on anyway. Yeah. So reset would operate on the branch. So if this was master and I reset head back 1, master moves back 1. The branch moves back 1. If I'm on master, it's got three layers. One is moving the head, and then the second is reset the index, the head, and the third is reset the working directory to head. Yeah, so we've got the 3 different layers. This slide is mainly here because I wasn't really sure who the audience were going to be. Checkout, similarly, without paths, it operates on the head pointer, not the branch. So if I did the same thing with checkout, head would move back 1, but master would stay in the same place. That's conceptually the difference. With paths, it works a little bit differently, which is, I think, probably where the confusion comes from, because you have the same command that does actually 2 fairly unrelated behaviours. It updates the index and the working directory of the specified files. So, part of me feels that it might have made more sense to have them with different names, but once you know it, you know it. So we've got other operations. Log, we now know, seems really trivial. We just walk back. We could probably write a script ourselves to do a git log now. Diffs, where they're just files. We know how to access the files. We know how to diff them. Stashing is actually just committing. Stashing is really interesting, actually. Stashing it creates 2 commits. So it creates one commit that gives you the state of the index and one commit that gives you the state of the working tree. So that when you put the stash back, it can restore them both. But the nice thing is that they're just commits, so you can just treat them like any other commits. They have parents, they have everything.
That answers a question I've sort of had for a while, which is why I have to sign 2 commits with my GPG keys when I stash.
Now you know. Amend, git amend or reset or anything that, or rewords when we're doing rebasing and we're changing things, all of those things that modify any of the metadata that we've seen before, we can see now that it would obviously create a completely new commit. So if I do a git amend, I can actually go back to the previous commit. Still, it's still there. It's not referenced. It's an endpoint that's not referenced by anything else. Yeah. I'll quickly maybe. Well, what I think I'll do at this point is, I was going to do a little bit more demonstration, but I'll draw it to a close. Thank you for listening. If there are any questions, I can go in and look at specific parts of maybe the merging or rebasing of things and how that affects the Git directory afterwards in the discussion. But yeah, thank you for your time.